All right, in the last video, we developed this new crazy, insane looking definition for the limit of f of x as x approaches a. It took a lot of work, took a lot of thinking, took a lot of crazy analogies. But this picture is really where we landed. And if you understand this picture and the dialogue that kind of goes on behind this picture, remembering that epsilon is like a challenger. Our goal is to prove that, or is to show that the limit of f of x as x approaches a is equal to L. In order to do that, we are challenged with a very small number epsilon right here. We want to imagine that to be small. And then we go epsilon away from L, create a horizontal line in both directions. And we want to see, or we want to show that the limit is equal to L at a, or as x approaches a, and the goal is we need to respond to that epsilon challenger. Our response to the epsilon challenger is this delta right here. And if we can shrink these green lines, I kind of imagine it as if we can shrink these green lines, perhaps they started out here or something. If we can bring these green lines in far enough to where this function f of x is completely within the yellow lines, then we can say that the limit exists. A few important things. Epsilon was arbitrary. We cannot care how small epsilon was. If no matter how small epsilon, we can always find a delta that works, then we can proclaim that the limit exists. So here's sort of just a picture of what's going on. Notice in pink, I have that all of those function values are indeed within the yellow lines. But this has been very theoretical this whole time. This video is going to be a lot more practice, a lot more, I don't know, whatever the opposite of theoretical is. I'm blanking on it right now. Practical? I don't know. So let's see this in action with specific function values instead of just vague f of x's, l's, a's, and stuff. What if I wanted, or let's say let f of x equal 3x minus 1, and let's say we want to find a delta bigger than 0 such that f of x minus, I'm going to be really, really intentional with my colors here, 5 is less than, let's go with 1/10. Again, I'm being intentional with colors. As long as 0 is less than x minus, okay, let me continue to be intentional, 2 from delta. Okay, so you should ask, what is L, the limit here? What is 1/10 represent? What does what does, I gave it away. What does 2 represent in terms of our official definition? This is a specific case, indeed. So this is our problem statement. I'll write example, and I'll write solution. What you could do at the beginning is say, oh, our epsilon is equal to 1/10 here. Our f of x is given to us as 3x minus 1. It looks like our a is equal to 2. And our L, the limit, is equal to 5. All right, so in this case, we know what this object is. So I think the best thing, at least for our first example, is to simply draw what's going on. We know how to draw that, so let's try it. I'm going to draw the first quadrant because we are apparently concerned around when x is equal to 2. Or around where x equals 2. Okay, and we have that the y-intercept is -1 and the slope is 3. So it looks like it's going to go something like this. So here is my a equals 2. And is it even true that the limit equals 5? Yeah, I think so. Apparently this height right here, simply by plugging 2 into our function, even though we're not allowed to do that, but when we're talking about the limit, it is going to be 5. So in other words, this limit is believable. Here's our function f of x equals 3x minus 1. And we want to create those yellow lines. Here's our challenge. This is going to be 5 plus epsilon, but that's also known as 5 plus 1/10. And here's this other line, the other challenger line, 5 minus 1/10. And, okay, my picture's not fantastic here. Actually, I think I should fix it because it should look a lot more symmetrical than I have it looking. Here we go. There you go. So all our task is to do, and of course we should also simplify these. 5 plus 1/10, what is that, 51 tenths? I don't know if we technically need to, actually. 51 tenths, yep. This is 49 tenths. We want to choose this distance. We can see it in the picture. We just got to find something that works. And you can use just basic algebra in this case. So that all of the x values within this interval, or I should say these intervals, because we're not allowed to step on 2, are bounded between those 2 yellow lines. That's easy because I think using algebra, we can find this intersection point. Like using algebra here, I'll use blue. No, this darker purple. We can also find this intersection point. It's not meant to be the one with the green. And then we just simply have to choose some value, and we can even find where these 2 guys intersect on the x-axis, or excuse me, the x values of those intersections, and then just choose a delta that's less than that. So let's do it. It's going to be a little bit of an annoying algebra question, but let's see. And you could also just logic this, but I'm going to stick to kind of brainless algebra. We are wondering for this line, for that purple point, the y value is such that 51, well, that's fine. 51 over 10 is equal to 3x minus 1. That's what this purple point is. Solving for x, that's going to be 51 is equal to 30x minus 10. Add 10 to both sides. 61 is equal to 30x. 30? Yeah, 30x. Divide both sides by 30. So x is equal to 61 over 30. And so we got this x value, purple x value, 61 over 30. Okay, so you could probably already guess. I think we could all probably already guess. This one's going to be, oh, maybe I can't guess. $59 over 30. Let's check that, though. So this would be when 49 over 10 crosses the line 3x minus 1. That's basic algebra. Welcome to basic algebra. 49 over 10 is equal to 3x minus 1. that tells us that 49 is equal to 30x minus 10. That tells us that 59 is equal to 30x. And that tells us that x is equal to 59 over 30, which is what I conjectured. So now I have to wonder, okay, so what's the distance between 2 and 61 over 30? And that is clearly 1/30. If you don't believe me, you can just do 61 over 30 minus 2. But my favorite way to say 2 is 60 divided by 30, and then conclude that it's 1/30. So we simply need to choose any delta less than 1/30. So I'll even write that. Therefore, here's my answer. Therefore, we simply choose any delta less than 1/30. For example, and bigger than 0. Delta must be bigger than 0. So I'll say, for example, bigger than 0. For example, how about 1/50th? Or 1/100th. And then let's show that that works. Then if x minus 2, okay, this is important. This is the most important part. We're showing that this delta works, is less than our delta. Let me use colors here. This is our choice of delta. Is less than delta, which is equal to 1 over 100. That implies, so another way to use this absolute value is swap this 1/100th to the other side, make it negative. Is less than x minus 2 is less than positive 1/100th. Indeed, if I have, like, for any values here, the absolute value of a is less than or equal to, or I'll use less than in this case, any, I don't know, 5, says the same thing. That sentence is the same thing as, so this is like a thought bubble. I'm trying to justify what I just did. -5 is less than a, which is less than 5. Those are synonymous. So I just used that same thing. I had that x minus 2 in absolute values is less than 100 or 1/100th. That says the same thing as this. But here's the thing. I want to show that if this is true, remind myself of my goal. I want to show that this is true. I've already supposed this is true. We found this delta. This is the problem statement. And I want to show, and we chose this delta to be 1/100th, and we want to show that as long as this is the case, then this is also the case. So we're supposing that this is the case right here, and we want to show that if this is the case, then this is the case up here. So we want to land at I accidentally muted myself. We want to land at f of x minus 5 in absolute value is less than 1/10. So how am I going to do that? Well, this is also a thought bubble. F of x minus 5, is equal to 3x minus 1 minus 5. That's the same thing as f of x minus 5. Remember what f of x is defined as. 3x minus 1. Oh, but that says the same thing as the absolute value of 3x minus 6. And that says the same thing as the absolute value of 3 times the absolute value of x minus 2. And so there you go, honestly. So what we could do is force this to show up and then go work backwards. There's going to be a lot of working forward and working backwards. So if I want f of x minus 5 to show up, I need this to show up. All right, so this is the real thing. I don't think we actually need this, but except that we're really close, because what I can do is multiply through everything here by 3. Oops, I said 3 and then didn't write it, because I want f of x minus 5 to show up. In other words, I want 3x minus 6 to show up. That's what I really want to show up. 3x minus 6, because that is f of x minus 5. So multiply everything by 3. Oh, look. There it is. Oh, but that says the same thing as 3x minus 6 in absolute values is less than 3 over 100. But here's the thing. We want to show that 3x minus 6 is less than, what was the original challenger? 1/10. But guess what? 3 over 100 is certainly less than 10 over 100, which is also known as 1/10. And I guess the last thing you can say is this is the same thing as, in parentheses, 3x minus 1 minus 5 is less than 1/10. And of course, that implies that f of x minus 5 is less than 1/10. So we did it. All right. So long example for the first one. I'm okay with the first one being a long example. Now, let's see. We could have done that without a graph. So let's try it without doing this whole graph. Even though this graph really is good for intuition, this next one I'm gonna pose a very similar question, and then we're gonna do it without the graph. So let me go down here. So this time let's do f of x equals 5x minus 7. And we want to choose a delta bigger than 0 such that, let's go with f of x minus, let's go with 13, is less than, okay, so what challenger do we want this time? Uh, 1/10 again? No, let's go more severe here. 1/100th. And okay, so what's gonna make this equal to 4, I guess? X minus 4 is less than delta. Okay, so this is our new question. And let's try to avoid a graph. Let's kind of lean on more like intuition. I color-coded only one of these. Here's our delta. Here's our A here. And here's our limit L. Noticing that is really important. And of course, f of x is the same thing as 5x minus 7. In fact, that's going to be my solution. I'm going to start with my goal. And here's what I mean by that. My goal is this inequality. That's what I want. I want to crush this object, x minus 4, so that this inequality holds. So how I'm going to do that is start with my goal and kind of force this object right here to show up. What must be true of this in order for this to be true? So this is my goal. Start with my goal. This implies that we have a name for f of x. I think it's, what was it? 5x minus 7. minus 13 is less than 1/100th. Oh, but that implies that 5x minus 20 is less than 1/100th. And remember, I want this object. I want this object to show up, and I think it's already pretty much here. We got lucky here. Truth is, you're not getting lucky. This will happen often. This is the beauty of limits and how things kind of just work. I can factor out a 5. I can use an absolute value rule. The absolute value of a product is the product of absolute values. Oh, sorry, I factored out a 5. You guys are probably looking at that going, yeah, he'll notice that. He'll notice that. This shouldn't be 20, guys. Why is it not letting me erase? Here we go. Oh, so look at what showed up. There it is. The x minus 4. There it is right there. But in this inequality right here, it's kind of by itself. So let me get rid of this 5. By the way, the absolute value of 5 is famously just 5. So we got x minus 4. This must mean that x minus 4 should be crushed to be less than 1/500. Oh, but wait a second. Let's just define this to be delta. So here's what we just did. We said, therefore, choose delta to be equal to 1/500. Then f of x minus 13, and it's going to look like I'm doing a bunch of the same steps again, and I kind of am, but it's really directly answering the question. We want this to be less than, we want to show that if this is the case, if x minus 4 in absolute values, or the distance between x and 4 is less than 1/500, then f of x minus 13 is less than 1/100. So let's just see. And here's the, here's sort of the idea. We want to show the reader that that is the case. F of x minus 13, and it's good. Like I said, it's going to look like a bunch of the same steps, but it's going to be really pretty. I think it's pretty. 5x, all I'm doing is replacing f of x, 5x minus 7, minus 13. That is the same thing as 5x minus 20. That is the same thing as 5 times x minus 4. But here's the thing. We chose delta to be equal to 1/500, and we forced x minus 4 to be less than 1/500. So what I can say here is that this object, I can replace this and say that, oh, this whole thing is less than 5 times, that x minus 4 in absolute values, we forced that to be less than 1/500. Oh, but look, that is the same thing as 1/100. And that's exactly what we wanted to show. Okay, now, we've been dealing with particular epsilons. Remember, this is like our epsilon right here. And this is our delta. We chose this delta based on the challenger. What we need to be able to do is deal with the abstract epsilon. All right, so this next one, we're going to take it up a notch. And in fact, at this point, we can officially do some proofs. So I'll go right here, maybe. Let's do prove that the limit as x approaches, 3, of 4x plus 3 is equal to 16? I'm just coming up with these, hoping it works. 15. That was almost embarrassing. Am I going crazy? No, that's good. That's good. All right. So we now, all of a sudden, we're not doing practice problems anymore. We're doing official proofs. And there is a mathematical tact that you have to hold if we are doing official proofs. Here's what I want to see. Before you actually write the proof, you want to choose your delta. So before you start the proof, you can write solution. I'm going to write solution. Notice I haven't started my proof yet. I'm just brainstorming. I'll even write that. Brainstorm. / find delta. Find a delta bigger than 0. But here's the thing. In this case, find a delta bigger than 0 such that f of x minus L is less than epsilon whenever this holds. But in this case, we have specific values for L and for A and for f of x. So let me point all these out. This is my f of x. This thing right here, that's my A. And this thing right here, that's my limit. So we need to find a delta such that, I'm going to rewrite this. In other words, we need f of x minus L, but we know what f of x is. That's 4x plus 3. We also know what L is, and that's 15, is less than epsilon. Notice that this is the first time we're not changing epsilon. We don't have a particular challenger. We need to be able to face any challenger. So we're keeping this abstract. We're saying, I don't care what you give me as a challenger. We need to find a delta that works no matter what. And in this case, we're going to find out that delta actually depends on epsilon. Notice that, like a second ago, the delta ended up being 1 over 500 when the epsilon was 1 over 100. Indeed, that delta was related to the challenger. So we want this to happen. But that says the same thing as we want this to happen. But that says the same thing. Oh, I'm doing bad math, you guys. I'm like, wait, this doesn't work. That says the same thing as 4x minus 12? Yeah, good. Is less than epsilon. But that says the same thing as 4 times x minus 3 is less than epsilon. And remember, we want this. We want to choose a delta for which to crush the distance from x to a, but remember a is 3. So we want to force x minus 3. Again, here's a, here's a. We want to force the distance between x and 3 to be less than some sort of delta, or we can choose delta conveniently. So what we really want is x minus 3 to show up. To see how much we bound x minus 3. Luckily, it has magically showed up in this inequality. So this, of course, implies that 4 times the absolute value of x minus 3 is less than epsilon. And this tells us how we want to crush the distance between x and 3. This implies that x minus 3, in order for this to happen, x minus 3 should be less than epsilon over 4. And indeed, that is going to be our choice for delta. So our response to an arbitrary challenger is simply to divide the challenger by 4 and then crush the distance between x and 3 to be less than the challenger divided by 4, which is also known as epsilon. And then that's our brainstorming. We found our delta. Now we can actually add it into our proof. So this is an official proof here. You always begin these types of epsilon delta proofs with let epsilon be bigger than 0. And this is us accepting a challenger. We are saying that, hey, give me any small number. Any small number. Let epsilon be bigger than 0. I don't care about how big it is. What I'm going to do is choose delta to be equal to epsilon over 4, which is, of course, bigger than 0. And I don't need to say that even. Then f of x, this is an easy peasy proof, minus L is equal to, and we want to show logic with this choice of delta. We want to show logic and hopefully land at this is less than epsilon. That's our goal. We want this to be less than epsilon. So let's see. Let's see how it works. We know what f of x is. 4x plus 3. We know what L is. That is going to be 15. So this is equal to 4x minus 12. That is going to be equal to 4 times x minus 3. And x minus 3 is the thing that we're crushing. We want the distance between x and 3 to be less than epsilon over 4. So I didn't mean equals. I meant less than 4 times, epsilon over 4. Oh, hey, look, we did it. Those 4's cancel. All we have left is epsilon, and this last part is the most important. Whenever, or as long as, either one, we force x to be close enough to 3, and we chose delta here to be epsilon over 4. You can write epsilon over 4 right here if you want, but I'm going to write delta. And that's it. And then we can say, therefore, the limit as x approaches 3 of 4x plus 3 is indeed equal to 15. And we've completed our proof. All right, that was huge. So it always starts with brainstorming. I'm going to do two more complicated ones. Things that are going to certainly get harder than this. I encourage you to, like, for instance, I can ask you, here's homework. This takes huge amounts of practice. Do not expect to watch one video and be a pro at this. This takes a lot of practice. Prove these. I can do the limit as x approaches 1 of 7x minus 8 is equal to. Notice you can easily write your own questions. You know what this limit should be. It should be -1. Try proving it. Try this one. The limit as x approaches -5 of 3 plus 2x. That should equal -7. Try proving it. You can do the limit as x approaches 2 of, let's go with 8 plus 3x divided by 4. And that should equal, I don't know why I'm making my job so hard, 7/2. Try proving it. Anyways, you can easily come up with your own questions here. But understanding the process and the idea is the most important. Let's try a trickier one. Let's ramp it up. Go right here. Prove that the limit as x approaches 2 of 3x squared minus 5x plus 4 is equal to 6. And here's my solution. In my brain, I should name these. Here's my L. That's L. Here's my f of x. And here's my A. So we want f of x minus L to be less than some fancy epsilon, whatever challenger is thrown at us. This is going to be significantly harder. It's going to take it up a notch, and there's going to be one step in here where you're going to be like, why? And it'll be a leap of faith. My answer to your why question will be because it works. But we'll see why it works. We need f of x minus L to be less than epsilon. But that says the same thing. Again, I'm not in my proof yet. I am brainstorming. This is 3x squared minus 5x plus 4 minus 6 is less than epsilon. Again, because I know what L is, it's 6. And I know what f of x is, it's this 3x squared minus 5x plus 4. Oh, but that implies that 3x squared minus 5x minus 2 is less than epsilon. Oh, but check this out. That factors. And we know that the absolute value of a product is the product of absolute values. Now, maybe you're noticing the problem. My goal here is this. I should add this literature. We need this to happen. In other words, we want to control or we want to crush this value, x minus a, which is 2 in this case, right? We want to crush x minus 2 enough. If you remember yesterday or the last video, we want to walk close enough to 2. That's what I am saying right now. But here's the problem. I see x minus 2. It magically showed up. So maybe I can get some sort of control on that thing. But the problem is we also have 3x plus 1. We want to crush both of these things. Now, here's the thing. We just need to find one delta that works. So here's what I'm going to do. I'm going to say, let's just suppose that we have the distance from 2 is less than, I don't know, some random number. Let's make it easy, though, 1. So we have walked so that we are less than 1 away from A. We want to see that if that is true, how small is this? Okay. We're wondering if this is true, how small is this? Or what does this look like? And you can use it on a number line, or you can think about a number line. So here's 2. And we are saying, so here's 1, here's 3. Our x values are living in here. If our x values are living in here, then what does this object look like? Well, the lowest x value that it could possibly be is 1. So it's this thing, this 3x plus 1, is at least this much. Right? Because I scooted this x value as far as it can this way. But the biggest x value it could be is 3. So it is at most this much. All right. So what that means is that this absolute value of 3x plus 1 is less than 10 and bigger than 4. But the only part we need is that this 3x plus 1 is less than 10. That's huge. Therefore, what we can say is that this implies that if x minus 2, the distance from x and 2 is less than 1, then 3x plus 1 is less than 10. So this implies that 10, or we want 10 times x minus 2 to be less than epsilon. And this gives us our hidden identity. Well, we have to choose. Choosing delta is going to be a little bit weird in this case. We also want x minus 2 to accomplish this task. If x minus 2 accomplishes this task, then this is accomplished. But we also need this. We need x minus 2 to be less than epsilon over 10. Why? Because then we can completely backtrack and land here. So here's the weird part. We kind of have x minus 2 crushed in 2 different ways. All right. Now, we just need to find one delta. By the way it looks like we have 2 deltas. That's a little bit annoying. So how do I find a delta that's going to accomplish both of these tasks? Here's how. We simply need to choose a delta, such that delta is less than 1, and that and is crucial. Delta is less than epsilon over 10. And you might ask why? Well, because if x minus 2 is less than delta, since this is true, it also is the case that x minus 2 is less than 1. The absolute value of x minus 2 is less than 1. But wait a second. We also have that if x minus 2 is less than epsilon tenths, or excuse me, is less than delta, then since delta is less than epsilon tenths, we would have that x minus 2 is less than epsilon tenths. So this delta, simply any delta, we need to choose a delta that is less than 1 and less than epsilon over 10. And you have to agree that since both epsilon over 10 and 1 are positive numbers, it's certainly possible to choose a number that's less than both of them. So this could be 1. Maybe this is epsilon over 10. Choose any number in here. That's our delta. Oops. That's our delta. But we don't know that epsilon over 10 is less than 1, so... But we do know it's positive. So perhaps this is the epsilon over 10, and here's the 1. So we just need to choose any delta in here, in that case. In either case, we can choose a delta that's less than both. And if we choose a delta that is less than both 1 and epsilon over 10, then this is true. And this is true. But the main key with this, if this is true, then this is true. Okay. So this was all, I haven't even done the proof yet at all. So let's see the actual proof. This was all brainstorming. Let's see how this works. Official proof. Let's go. Uh, 3x squared minus 5x plus 4. I got to remember that because I'm going in. How does the proof begin? We let epsilon be bigger than 0. And then we choose our delta. We choose delta bigger than 0 such that delta is less than 1. And remember, 1 was arbitrary. It just happened to be convenient. It could have been anything. And delta is less than epsilon tenths. We wanted to choose a delta because we did all the work and we showed ourselves that this works. Then we could do this. Then if x minus 2 is less than delta, that would imply that x minus 2 is less than 1 because of this. And remember, I'm saying if. Oh, but that implies that negative 1 is less than x minus 2, which is less than 1. Oh, but that implies what I'm trying to do right now is force 3x minus 1 to show up in the middle here. So here's how I can do that. Multiply everything by 3. And then I need this to be a plus 1. So how do I get there? I add 7. And then this, of course, says the same thing. Negative 10 is less than 4, so we can write this. And, of course, that is synonymous with this. So what I just said was this. If x minus 2 is less than delta, then 3x plus 1 is less than 10. That's what I just said. Based on this delta that I've chosen, since delta is less than 1, then x minus 2 is less than 1, if x minus 2 is less than delta. But if x minus 2 is less than 1 in absolute values, then the absolute value of 3x plus 1 is less than 10. But also, and here's where the magic happens. If we crush the distance from x and 2 to be less than our particular choice of delta, this inequality is about to be really useful. I don't want to use that color. This color. This inequality is really useful. And this inequality is accomplished if we force this to happen. If is the biggest word in mathematics. If x minus 2 is less than delta, then this is true. Also, if x minus 2 is less than delta, then this is true. And this is going to take us home. Therefore, I'll write f of x minus L. And you don't need to write the f of x minus L, but I'm doing it for clarity at the beginning, which is equal to, okay, I got to remember what f of x is. I forgot it. Oh, man. 3x squared minus 5x plus 4. Minus 6, which is our limit. This is equal to 3x squared minus 5x plus 4, or excuse me, minus 2. That is the same thing as 3x plus 1 times x minus 2. That is the same thing. Oh, but here's where the special thing happens. Remember, if we force x to be close enough to delta, or excuse me, close enough to 2, then we have this. So we know that 3x plus 1 in absolute values is less than 10. If we force that to happen. And at the end, we're going to say we did force it to happen. But wait a second, we also know this. So this is less than 10 times that x minus 2 in absolute values must be less than epsilon over 10. And remember, we want to force this distance to be less than epsilon. And this is where we are victorious. 10s cancel. This equals epsilon, the most important part right here. Whenever we are close enough to 2. How close? Delta close. With our specific choice of delta. We chose a delta such that delta is less than 1 and delta is less than epsilon over 10. If that is the case, then 3x plus 1 is less than 10 and x minus 2 is less than epsilon over 10. And if both of those are the case, then f of x minus L must be less than epsilon. That's what we wanted to show. And therefore, the limit as x approaches 2 of 3x squared minus 5x plus 4 minus 6, or excuse me, is equal to 6. And we've completed our proof.